Welcome back, everybody. We're going to go over the free response for the Unit 6 test on thermodynamics. This first question was taken directly off the Form A 2007 test. We're going to go through it. Question A asks us to calculate the standard free energy change, delta G. I do not see a little f, so the only other equation I have for delta G is delta G equals delta H minus T delta S. If I saw the F, I could have done a products minus reactants. I'm going to plug into this equation. I'm going to get my delta H from up here. So this is going to be equal to negative 264 minus my temperature. 298 Kelvin is seen here. 298 Kelvin is seen here. 298 Kelvin. And I'm going to multiply that by my delta S. Beware, it's in joules, so we're going to have to divide that by 1,000, giving me negative 0.278. My answer for this is going to be negative 181.2 kilojoules per mole. The Kelvin here canceled with the temperature in the equation to give us an overall unit of kilojoules per mole. Next says, determine the temperature at which the reaction is at equilibrium. And it tells me that at equilibrium, delta G equals 0. Well, my only equation which does involve temperature is right there, my delta G equals delta H minus T delta S equation. So I'm going to call that 0. I'm going to plug back in delta H, which I know is negative 264. I'm going to then plug back in my numbers, 298, negative 0.278, and I'm going to get a temperature value of about 949.6 degrees Kelvin. Very important to put the units. Now, a lot of people have been telling me this is an abnormally high value. Yes, it's high for water, but for most other substances, this is actually a fairly reasonable temperature. Keep in mind that substances like copper don't melt until the upper end of 2,500, 2,600 degrees Celsius. Remember, steel doesn't melt till above 3,000 degrees Celsius per the thermite demo. So this is a reasonable temperature. Water is definitely going to be a gas, but there are other things in the world other than water. C asks us to calculate delta H when 2.56 moles of NF3 react are formed from N2 and F2. Well, this goes back to our balanced reaction. Let's not overemphasize the difficulty of this problem. It's pretty easy. It's just a ratio. According to the mole ratio, every time 2 moles are produced, we get that much heat. So every time 2 moles of NF3 are used, we get negative 264 kilojoules. All right, that's going to cancel out. We're going to get our answer, negative 30, around negative 34 kilojoules per mole. A lot of people tended to miss this one. Just set up a proportion. Another way to do that is you could say 0.256 is to what as 2 is to negative 264. You could cross multiply. This is a way of doing conversions if you do not like the bubble method. All right, D, we're talking about bond energy if you read the problem. Breaking bonds, the word's showing up, bonds. So our old equation is really going to come in handy on this problem. This asks us if you have 2 NF3s, how many bonds do you have? Then it goes on to ask the shape and the hybridization of NF3. All right, NF3 is going to look like this. If you need help doing Lewis structures, feel free to come in class and ask me. All right, one of them has 3 bonds, so total 6 bonds. They're all sigma bonds. The shape of this molecule is going to be trigonal pyramidal. And the hybridization is going to be sp3. There are 4 total things. Thus, we have 1 from the S and 3 from the P's needed to hybridize. Don't worry, this was an extra credit problem. All right. Use the information to calculate the bond enthalpy values below for the FF single bond. They want us to fill this in. Normally it would be filled in. So in this case, they are asking us to use our broken minus formed equation. Okay, they must have given us the overall delta H, and they did. There it is. So negative 264 is what I'm going to set this all equal to. Negative 264 is equal to the sum of the bonds broken. Okay, so we know that one of these was broken. And we know that 3 of these were broken per the balanced reaction. And that's what we're actually solving for, so why don't we call that 3x minus, and this is where people messed up, 6 of these bonds. That's why they asked you that question right there. Getting your minds wrapped around that value. When you plug this all in, x, which is equal to the FF bond, is equal to 140.67 kilojoules per mole. You guys could round that however you like. I'm not a stickler for significant figures. Moving on to question number 2. Okay, they're showing us a phase change in this question. Here we got a puddle of water, and here we got a cube of water. Helps to draw out a picture. It's asking for delta G at room temperature. We know that water wants to be a liquid at room temperature. So the formation of freezing water at room temperature is going to be a non-spontaneous process. Okay, it wants to be a liquid at room temp. Predict the sign of delta H. Okay, this again is a tricky situation. I take blame for this problem primarily. It gets colder, and I've told you that reactions that get colder are endothermic. However, this is a phase change, not a reaction. So in order for a puddle of water to freeze, it has to release heat, making delta H less than 0. Tricky question. An easy way to think about it is, in order to melt an ice cube, you'd have to put heat in. So it's the reverse of that. All right, so we have a non-spontaneous exothermic reaction. Delta S is getting cleaner. You can see from this diagram above that if I had a puddle, a cube is definitely more ordered than the puddle. This is the solid, here's a liquid, here's a solid water. What effect does temperature have on the spontaneity of this reaction? Okay, we got to bring in an equation that involves temperature then. Okay, we know that this is negative, and we know that this is negative, making this positive. So if temperature equals 0, this is out of the ball game, and delta G is negative, it's spontaneous. And if temperature goes to infinity, this side's going to win. Delta G is positive, it's non-spontaneous. Basically, when it goes to 0, this is going to be the value. And when it goes to infinity, or a very high temperature, whatever that is going to be the value. How would lowering the EA influence the rate? Okay, well, let's draw our picture first. This is energy, time, lowering the EA.
Are you drawing them?